Okay, everyone, so it's time to start, and I apologize for not being here. Last time I had a big emergency. I fell down a flight of stairs, 11 stairs, onto my head. Couldn't remember a thing, couldn't even remember where I taught, what I taught, where I taught. I was on my way here. I was like, it was right before just in my house, right before I was getting ready to come here. And couldn't remember anything. So I went to the emergency room, and about, a few hours later, I regained my memory and all. And, but I don't know. I think I'm fully recovered. They just say don't fall again. So I just had a concussion. So sorry about that, but I hope you all watched the lecture online. That was from last semester. So we're going to pick up here on chapter 23, because I posted 22 already. So we'll start here on 23. But if you have any questions or anything, just interrupt if something wasn't clear in the lecture. All right, so let's go to the document camera and get started. Oh, also, pick up your exams right now if you haven't already. They're right here in that folder. So you can come right up. They're right here. So you can come up and get them. They're not in alphabetical order, but. So let's look at where the exam key is. So you have your exams, and you either have, look in the header, and it either says Feb or February. So that's the code for which exam key you have. So for example, if you have February, it's going to have February up here on every page. And the explanations are all here. Now, the exams themselves that you picked up, of course, aren't graded because your Scantrons were graded. But it's actually better to get your exam because most of you, wrote on your exam your thoughts, some work, and you can go through it and count up how many you got right and make sure that's what's on Compass right now. That's where your exam scores are posted. So that's the February one, and then the Feb is the same except slightly different. Okay, any questions on that? And if you have any problems with how it was graded, just come see me during office hours. Now, those of you at home or online, just come to office hours to pick up your exam. You can come 2 to 5 any day, except do it before spring break. So once spring break, let's look at when spring break is. We're going to not have them available. So anytime before spring break, come and pick it up. Okay? All right. So any questions on that? All right. So let's go to the document camera now then. And we're going to start right here on looking at errors around the regression line. So last time we talked about the regression line as the best prediction line for predicting y, in this case y's finals, from x. And of course, it's not all the points. Each point in this case represents the exam represents a student in a Pass Stat 100 class, and their score on the exam and the final, their exam average and the final. So that's what this represents. And here is this regression line here. And then, of course, the regression line doesn't make a perfect prediction. There's scatter. For example, this student right up here did very poorly on the exams, but he did much better than expected. This is the actual score here. And right here is the predicted score for that particular student. And this distance right here, that distance, the actual minus the prediction is called, well, it's called the prediction error, right? Or the residual is another word for it. And this person has a positive residual because they're above the regression line, whereas this person, B, whoa, look how low he did. And he was expected to do much better. The predicted's there, and the actual, this is a negative residual. The actual minus the predicted is a negative number. This minus that. Okay, so that's the prediction error, also called the residual. And now, often what you'll see, I mean, it's you could get the distances from here. You just read off the y value, the actual y value minus the predicted y value. But sometimes it's easier to look at something called a residual plot, a scatter plot of the residuals. So what is this? This has x, the same x exams, but here what it does is just show the errors, just the residuals instead of y. So it's always, the average of the residuals is always 0. That's the average of the residuals is always 0. So it's easier to read the size of the residual from this plot. Also because you can expand it. You just have to, here, you can make the scale bigger so you can see it better. So for example, here it's much easier to read this. You can read this distance right here. Just write, like, let's say that was 18, so you could read it right off the graph rather than trying to, subtract those two. So it's easier to do. And so same with this one. That looks like it's like -9 or something, and this one, which looks like about -25. Okay. So that's all that's doing. And any questions on that? Okay, so for any, as I said here, for any regression line, the average and the sum of the errors is always 0. This should sound familiar to you. It's like the deviations from the average. The average is always 0 because the negatives and the positives cancel out. And the standard deviation of these residuals is a good measure of the typical size of the error. So the standard deviation, it's also called the square root of the mean or the average of their squared errors. That's how you figure out a standard deviation. And it's a typical spread. Okay? So instead of, though, figuring out the standard deviation, remember how you do that? We can write it up here. So the standard deviation of the errors, remember what you do when you figure out any standard deviation? You're going to sum up, you're going to take, first of all, the deviations from, in this case, what is it? We're taking all the errors. So we're taking for each y, let's say there's n of them, for each y, we're going to subtract off the predicted, its prediction, right? Those are the residuals. And then, but since if we just summed up all those residuals, it would equal 0. So instead, what we do is we square them, like we usually do, right? And then take their average. But then that's the average of the squares. So we want to take the square root of that. So here would be the summing them all up and taking the average of the squares. That would be from I equals 1 all the way up to n of them. If there's 100 points, it would be all 100 deviations squared. This is the average of the deviations squared, which is the variance of them. But we want the square root, so it looks like that. Okay? And that's the same as, it's also called the root, the square root of the mean of the squared errors. The root mean squared errors. Okay? Each one of these is an error squared. Take their mean and then take their square root. So that's, now, that would be hard to do. Think about, yes? Say that again?
Shouldn't we change the residuals of B and C in example 1? I think they're like, aren't they reversed? B is.
Oh, yeah, yeah. She's right. Thank you for pointing that out. I made a error here. Let's go back, thank you. Right here, B is the big one and C is the small one, right? So these two are reversed. Thank you very much. Come up after class for the extra credit point for doing that. Thank you. This is the big one, and that's the small one. Thank you. All right, so now we're back down here, right here. Right? That's the negative 25, and that's the negative 9. Sorry about that. Okay, so now, does everybody understand this formula here? You got it? Okay, so look, would you really want to figure that out? That would be really hard to do. You'd have to take each one of these, get their errors. So there's a very simple formula that's very useful, a shortcut way of doing that, and that's right down here. There's an easy formula for computing that. And it's the square root of 1 minus r squared times the standard deviation of y. And it makes sense at the, I'm not going to prove this, but it makes sense to think about it when r is equal to 1 or negative 1 and when r is equal to 0. Let's see how that makes sense. Well, if the regression is perfect, right here, when r is equal to 1 or negative 1, then there's no error, right? Let's draw a picture of it. There'd be no error. If we were just in the positive quadrant here, every single point would have 0 error. It's on the line. This is when r is equal to either plus or minus 1. This is plus 1, minus 1 would just be pointed down. All right, so that's no error. That means that the standard deviation of the errors would be equal to 0. All right, and if you plug in, does that work in this formula? If you plug in a 1 or a minus 1 for r, you're going to get 1 minus 1, which is 0. So get 0 times anything is 0. So that checks out. How about, so that's a picture here. Okay, how about here? When r is equal to 0. When r is equal to 0, what would that look like? Well, let's think about it. When r is equal to 0, let's just go in the positive quadrant here. When r is equal to 0, it would just be random scatter. Random scatter. Knowing what x is wouldn't tell us anything about y, and our best prediction when r is equal to 0 would just be a flat line like this through what? The average of y. Y mean? It would just be the flat line like that. Okay? Because we would, no matter what x is, our best prediction for y would be the average of the y's. So what would be the typical spread around the average of the y's? What's that called? The typical spread around the average of the y's is the standard deviation of the y's. Okay? So when r is equal to 0, that would mean that the standard deviation of our errors is simply the standard deviation of y, just the typical spread around the average of the y's. And does that fit here? When you put a 0 in for r, you get the square root of 1 times the standard deviation of y. So that's the range that the standard deviation of the errors can be. Of course, it's always positive, and the smallest is 0, and the largest is the standard deviation of y. So that's here, this picture. So I hope that helps you remember this. Any questions so far? Okay, so the r squared that's featured in here, 1 minus r squared, is known as this coefficient of determination. That's what it's called. And what it is the fraction of the variance of y that's predicted. R squared is the fraction of the, okay, so this is, I don't know if you've heard this before, it's called this, and it's widely used because it's the fraction of the variance of y that's explained or predicted by the regression line. So you can just see this by squaring it. We said this, if you square both sides, standard deviation of the squared, that will give you the variance of the y, of the errors. And you square this side, and you get 1 minus r squared times standard deviation squared is just the variance. So 1 minus r squared is the fraction of the variance that's in the errors. So that means r squared is the fraction of the variance that's predicted by the regression line, and 1 minus r squared is the fraction of the variance that's left in the errors. So this is going to be important because this r squared is a key statistic in when we look at multiple regression. When we have this capital R, is just in simple regression, these two things are the same. Capital R is referred to is a more general term that's used for multiple regression. And so we're going to be using this something called analysis of variance to analyzing the variance, partitioning the variance into two parts, one that's predicted by our regression line or by our model, and the other that's left in the errors. And so this r squared, which is the fraction that is in our predicted by our model or explained by our model, is an extremely important statistic that we're going to be looking at all the time. And in simple regression, like that's what we're in, just 1x predicting 1y, it's the same as little r squared. Okay? So that's to come. So now let's go back to the scatter plot that we looked at. Did we look at this before? This is the same as what's on the previous page. Okay? This is, and what it shows is the exams and final scores of just 107. This is years ago, way back before you were born. First time I taught Stat 100. So, or maybe not the first, but one of the times. Only 107 students in the class. Now, Stat 100 has just, I don't know, probably something like 3,500 a year or something, or more. So here's back when it had 107 total, and here was our exams and final scores, real data. And so last time we looked at how to find the slope and y-intercept for the regression equation. And I hope you remember how to do that. So you have to, first of all, let's just look. Which one is the regression line? The regression line, there's two lines pictured here. And do you know which one the less steep one is? Do you know which one that is? Which one do you think the regression line is? This one? Say yes if you think. Okay, yeah. The less steep one is always the regression line, and the steeper one here is the standard deviation line. And where they cross is the point of averages. Okay, so that's the point of averages. It's given right there. What is it? Okay, now how do you know which is y and which is x? Well, it tells you here. So this is y and this is x. In general, if you're asked to predict, whatever you're asked to predict, that's y. So y is always the variable that you're predicting. Don't expect that x is always on. I just put those in arbitrary order. Okay, so in this case, that's what it looks like. So this point right here where they cross is the point of averages. So that would be the average of the x's and the average of the y's. And that right there is the point of averages. Okay, now we want to find the slope and the y-intercept. And you need to know this equation, the slope. I think it's pretty easy to memorize. It's the correlation coefficient, R, times the standard deviation of y divided by the standard deviation of x, rise over run. So in this case, we have to look up here. We're using this and these two standard deviations. So it's going to be 0.6, and just make sure it's, which get that ratio right, it's y over x. So it's 10.3 divided by 9.2. And that's equal to 0.67. So there's our slope. Now, how do we get the y-intercept? Well, to get the y-intercept, what should we do? Well, let's just look up here. So what do we have so far? We have our y, we'll just say finals, is equal to, now you're usually used to putting the slope first, but in statistics we put the intercept first, and then we put the slopes because we're going to get, we call this like, the intercept is b not b0, and then our first slope is going to be b1, so it'll be 1 times exams times x1, and then as we add in multiple regression, we keep adding these slopes. That's what we're going towards. Pretty soon we're going to do that, and so we'll have b1, b2, b3, etc. So that's what it looks like here, and right now we're predicting this line right here, y, and there's a lot of scatter around it, so this is our predictions, all right? It's our predicted. So that's what we've got, and now we've got b1 right here. This is our slope, b1 here, and let's fill that in, 0.67. So that's our equation so far. And now we just want the intercept. Well, you remember, for any line, this is going to be, it has to be, this equation has to be true for every point on the line, and the only one we really know is the point of averages. So that's the one we're going to plug in. We know that's on this line. So for finals, we'll just plug in the average final, and then we can solve for our intercept here. Same for the exam. So the average final is 73.6. That's what we're plugging in here. Plus equals, the intercept we're trying to solve for, plus 0.67 times, what are we going to plug in here? What do you think? The average for the exam's 83, right? So average exam, 83. That's what we're doing. And then we just solve for it. And I got that the intercept is equal to approximately 18. So that's what I'm going to put in there, and there's our equation. So to solve, just reminding you, to solve for the intercept, plug in point of averages. And that's what we got, 18. So there's our slope, and there's our intercept, and there's our equation. Now we're going to use this equation to make predictions. All right? Use the equation to make predictions. All right. So our predicted final is equal to 18 plus 0.67 times, what are we going to make a prediction for? Somebody who has an exam of 90. So I got 78.3. That's the prediction. You might think, oh, that sounds so low. We got a 90, and then, but look at the average for the final is low. So he's still above average here. Okay, so now Now, of course, do you think that prediction will be exactly correct? No, there's scatter around the line. Of course not. So we want a way to say, give or take about how much, to put error bars on that. And that's where we're going to use that standard deviation of the errors, the typical spread of the errors, to put error bars around that, to put some wiggle room around our point estimate. Okay? So what is the standard deviation of the errors? We're going to use our handy formula here. So the standard deviation of the errors, also known as the root mean square error, is equal to standard deviation of the errors is like standard deviation of y, but it's going to be reduced by some amount. So to remember it, just say standard deviation of the errors, you're going to have standard deviation of the y, but it's going to be reduced by some fraction here. And that fraction is the square root, a number less than or equal to 1 minus r squared. That's what it is. Okay? That number is always going to be between 0 and 1. And in this case, we have 0.6 here, so it's the square root of 1 minus 0.6 squared times the standard deviation of the y's, which is 10.3. This one we can do in our head, right? 1 minus 0.36, so that's 0.64. Square root of 0.64 is 0.8. So it's going to be 0.8 times 10.3. So that's how much it reduces it by. And I got 8.24. So that is the margin of error we're going to attach to it. Okay, so let's attach that margin of error. So now attach the wiggle room to the estimate. Okay, to give your estimate a range. Okay, so what was our estimate? Our predicted was 78.3, and we'll add and subtract 8.24, which will bring us, if you want to give it a range, it would be 70.06 to 86.54. So now it says, suppose the student really got, let's change this so we can, really got a 75 on their final. What is their residual? So which way do you subtract it? The residual is the actual minus the predicted. This person's below what's predicted, so it'll be negative. So just remember the residual, our prediction error, is equal to the actual minus the prediction. So that's the actual. Which is equal to 75 minus the predicted is 78.3. So this person is negative 3.3. That's the residual. And the typical residual is about 8.24, so this person it's a pretty good estimate for this person. All right, let's look at this. Now, sometimes you'll have, if you have a scatter plot that has sort of an elliptical shape, then we can use those where there's basically a normal distribution of these errors with any vertical strip. So for example, like we were looking at people who got a 90. So if you take like a vertical, I'm going to make it bigger, but imagine a vertical strip around here, and then you have the prediction with 78 point something, but within each little interval, there's like a normal curve, like centered at the prediction. If it looks like roughly like that, so this is our regression line right here. And right here is plus 1 standard deviation of the errors. And this is plus 2 above it, 2 standard deviation of the errors. This is minus 1 standard deviation of the errors. This is minus 2 standard deviation of the errors. So when you have something like this, then you can say, well, you know, between 1 and -1, 68% of the points are about, and between, you know, yeah, between 2 and -2 would be 95% of the points. It would look like that. We can look at this data if you want. This data is on our, you might be interested just to, why don't we quickly look at it? So we can go to the PC here. And let me pull it up for you if you want to see it. So let's see where it would, let's go to our, up here and find our data program. And then go here. And now we're going to choose this data set that's called the grades, I believe, under T. Yes, the grades. All right, and there is the students. This is how their grades were distributed. Okay, so now let's look at the scatter plot. And we have exams on the X and final here, and it should be the same thing. So let's see if we got the same equation. We did some rounding. So here, where's the regression? There's our regression line, and there's our standard deviation line. There's that point of averages there, and you can see the stats. So we did some rounding here. We rounded to 0.6. We rounded this to 83, but we got something roughly very similar to this. We got the finals equal to 18 plus 0.67 times the exams. We got for our standard deviation of the errors 8.24, very close. So that's the idea. Now, and here's the errors. The average is 0. There's the standard deviation. And there were 107 students. Now, what I was doing here, let's get rid of this SD line for a minute. I was looking at between 1 standard deviation of the errors in either direction. That's about 68% of the points, and between 2 is about 95% of the points, roughly. And before we did that, we looked at the error plot, so we could do that. So this is the error plot. So you see how the average is 0? And there we can say, okay, if you go up 1 standard deviation of the errors, you're going up 8.25 and down 8.25, and there's 2. So what do I mean by these? I think I can, basically that this normal distribution in between, let's go to any questions on this? We'll go to the, back to the notebook. All right, so let's go back to the notebook. And so what I mean is, like, what do you mean by normal distribution here? Well, there's hardly any points here, right? There's hardly any. But when you get to a place where there's some points, like let's just draw a strip here, you can see that most points, when I draw this normal curve, what does that even mean? It means that, remember what the height means. I'm just drawing it at an angle here. It would really go above like this, but I can't, I'm drawing it in 2 dimensions. And what I mean is that the points are gathered most closely around 0, around the prediction. And then as you spread out, there aren't very many of them. That's what I mean. So really, you should have a normal curve that extends up in another dimension. That's what I mean. That the points, most of the points are around 0. About 2/3 of them are between 1 standard error below and above. Now it's not always true, but when it looks like this, we're going to be able to use more robust statistics to analyze the data. So for example, we can use the normal, we can say, because it looks pretty good here, we can say that about 68% of the times our predictions of final based on exams will be right to within what? 1, because 68, 68 has z-scores of, I just did it here, So between 1 standard deviation of the errors, which we just said was 8.24 points. Okay? And 95% it will be within approximately 2 standard deviation of the errors. So, so that would be what? Within 2 times 8.24, which is 16.48. And about 82% of the time, what if it's 82? Just to remind you how to do this, we're just looking at critical values, Z star. So we have to go to our table, and 82. So we'd look at the area for 82, and if it's going to be a little bit less, 1.35, but generally speaking on exams, I say you can just round to look, this is pretty approximate. I don't want to use measures that are, so we'll just use 1.35. It's fine to just go to the nearest line, 1.35. So we'd say, so all we're doing here is we want to get this Z star here for 82%. So we looked at the normal table and we just saw between negative 1.35 and positive 1.35 is what we want. So that right there would be 1.35 times 8.24. And I got 11.12. Okay. So that's the idea. Any questions on that? These are our Z stars. Okay. Now we're going to start doing some inference. So far we've just been acting like we had the whole population. We did have the whole population. But what if those students were randomly chosen from a larger population of students, and we wanted to put estimate the regression equation and the slope for that larger population. So we want to start doing what we're going to do is we're going to put confidence intervals around the slope, and we're going to do significance tests for the slopes, just like we did for means. So that's what we're doing right here. We're going to start right now. So let's do that. So we have to make some assumptions first of all. All right. So we have these. So if we randomly sampled our data from a larger population, then we can use our sample regression estimate to estimate the population regression estimate, and then we're going to be able to compute standard errors, confidence intervals, and perform hypothesis tests. So we're going to that's what we're moving into. And we're going to do it first for simple regression, and then we'll do it for when we add more slopes. So, but in order to do that, we have to make some assumptions. Okay, and there's 4 basic assumptions. The first one is linearity. If we're going to just that our scatter plot, it follows a linear pattern. We don't want to end up using a regression equation for a line when we have a curve. When we have data that follows a curve, we want to use a curve if the data follows a curve. So we want to look and see if our data follows a linear pattern, linearity, and then we have to make some assumptions about the errors and around our regression line. And they're the usual ones of independence. You don't want one error to depend on the next error, right? We don't want them linked to each other. We want independent random draws. And another one is equal variability around the regression line. We don't want huge errors around part of it and then tiny little errors around another part of the line. And then finally, normality, which is what we just saw. If we have normality, we'll be able to use, for example, a t-distribution, because remember the t depends on normal population. And right now our population is the errors around the regression. So so in order to use a t-distribution, we're going to have to use normality. All right, So those are our assumptions. And as usual, we're going to use the usual notation. We're going to have to be a little more careful now to use the Greek letters for the population. And that's our ideal model that we're trying to estimate. And then the Roman letters for what we get in our actual sample. All right. And then we use those little hats that we've been using a little bit to indicate our predicted values. All right. So our model right now is just, we have 1x, right? Just 1x right now. And we have, our model is in the whole population, we're using these Greek letters, beta, instead of the b's, and plus error. So we're predicting, we know there's error around our regression line. So the errors are independent, normally distributed with equal variance. You've seen that, I'm sure, if you've taken upper levels statistics classes, you've seen IID 0 sigma squared all the time for the errors. That's same thing. Now, here's our sample regression that we've got in our sample. So we don't have to put the little errors around it because if we put a hat here, because we're saying our predicted y, that's on the regression line, is equal to, and this is the sample intercept we got plus the sample slope we got. That's how we can write it. We don't have to put errors if we have that little hat on there because we're just talking about what our predicted y's are. Okay, that's what that is. So now let's suppose that same data set we had, that we just got the sample regression. We thought it was the whole population. It really was the whole population. But let's suppose that the scores of those there were 107 students, but just pretend they're 100, okay? Of those 100 students from the previous example on page 113 were a random sample from a much larger class of Stat 100 students. Let's pretend 2,000, okay? So this is our little n. That's equal to 100, and we're going to take it from a huge population, big N, equal to 2,000. Now, how could we use our sample slope in our regression equation to estimate the population slope? So here's our sample statistics. So now we have to set up a box model, like we always do, a probability model, and imagine what? Imagine a much bigger population, a scatter plot. Let's imagine this population scatter plot that has inside here, this is the whole population. We still have exams predicting the final, but now we don't have, now we have like, 2,000 points, right? Lots and lots and lots of points. So I'll say we have n, big N, equal to 2,000 points, one for every student. One for every student in the population. Okay? There are 2,000 students in the population. And what are we doing? And so we have this, and we have this regression line. But we don't know it. Okay? We don't know it. And then what we do is we randomly draw n equals 100 points and get these sample statistics. That's all our sample stats, okay? That's what we have. Now we want to use this, so then what is it? So now we say, okay, so what do we do? Let's say we really did this, we drew. So now what are we going to do? How do our assumptions fit in? Well, first we have to, what we do is we'll look at our plot that we got, our sample plot, the one we just saw, right? And see if it would fit like a straight line with scatter. What do I mean? So you check for linearity. This is our first assumption. So let's say, so we get that plot we got, which looked pretty good actually, we saw it. So we get that plot, it's the same one we had before, and it looked, it looked okay. It looked like it didn't, let's say, okay, it looks pretty good like this. What are we doing? We're checking for linearity. What do I mean by that? This is good. What would be bad? Bad would be something like, that happens a lot. You could see something like, that, something that clearly followed a curve, and it's not. This, we wouldn't want to fit a line to something like this, or something like that, let's say, I don't know, there's lots of different possibilities. But if you see some pattern that's not linear, you don't want to fit a line to it, right? So this would be bad. It would violate linearity. This would be bad. It would violate linearity. Just mean that you're not going to try to fit a line if you clearly have a curve. So if it shows curvature, you want to fit a curve. If plot shows curvature, and a lot of plots do, we'd do a better job fitting a curve. We're going to deal with stuff like this later in the semester. But for now, let's just say, so it's good. So that's the first thing we do. So then if it's good, what do you do? Well, then if the plot looks linear, find the slope and the y-intercept. We've already done that. So we did that already on page 113. That's what we did. We'd do the same thing, and we'd get the predicted final equals 18. Let's say we got that plus 0.67 times the exams. All right, so that's our sample regression equation. All right. So now what's the next thing that we're going to do is we're going to look at, now each time, think about this, each time you take a sample from here, you're going to get a different plot and a different sample and regression equation. You'll get a different slope. Our slope's going to vary, right? Every time we do it, this is just one particular slope we got, and we got the slope of 0.67. So we want to put error bars around that saying, well, how much is it going to vary, right? How much is it going to vary? Like if we just took 2 points, well, if we took 2 points, we'd get a perfect slope of 1 each time. Let's say we took 3 points or 4 points, just a few points. We could get a perfect correlation, or we could get a negative correlation. It would vary a whole lot, right? If you just randomly took 3 or 4 points from here. Just think about it. You could take that point, that point, that point. You could get a negative correlation, right? So the more points we get, the more points, we'll have less error. And also, the other thing is, if we had a perfect correlation, well, then we'd get, imagine we had a perfect correlation or very little scatter, then we'd get very little error. So that's what we're going to think about, a way to describe how much the sample slope's going to change. So that's what we'll do here. So our sample slope right now is the best estimate of our population slope, right? What else are we going to use? But of course it's not exact, since each time we take a sample, it's going to vary. That's what we just talked about, right? So how much, by give or take, so it follows its own standard error law. How much the sample slope typically varies is called the standard error of the slope, because now we're talking about random variables that change, numbers generated by a chance process. So we're talking about standard errors instead of standard deviations like we did before. And again, it's going to follow its own square root law. Square root of, the bigger the sample size, the smaller our error is going to be by the square root of n. So it follows its own square root law. And for small n, we're going to have to do SE plus, right? All right, so let's just look at this. So here is, right here, is the formula for it. And let's see if we can make sense of this for the standard error of the slope. I think it really does make sense because it depends on two things, right? The variability of the slope comes from the random errors around y. If we had a perfect correlation, then every single sample would be a perfect correlation. If all the points followed a line, then all our sample would be. So the bigger the spread, the bigger the error around the prediction line, the more variability there's going to be in our slopes. So that's the standard deviation of the errors. Makes sense. But, and then also the bigger our sample size, the smaller our sample slope's going to bounce around. The smaller the error. You know, if you just have that's what we talked about before. We're going to get more accuracy with a bigger sample. And it's going to follow the square root line, square root law, like that. So why do we have this down here? Why doesn't it just look like that? But this is just because, maybe you can see it why do we put this here? Because, remember what the standard deviation of the errors is? It's the square root of 1 minus r squared times what? The standard deviation of y. The reason we need SDX is because slope is SDY over SDX. It's rise over run. The variability is described in terms of y, and the slope is change in y per unit of x. So we have to have this SDX to make the units match up. That's why we have it look like that. So, but the idea is that you have these standard deviation of errors, more spread, bigger standard error of the slope, and divide by the square root of n. But then you also have to factor in that, remember your units, and put the SDX in. All right. So now, what did I say? If assumptions 2 and 3 hold, why do these, in order to figure out this, in order to use this, you're assuming what? You're assuming independence, that's assumption 2. Like any standard error formula like this, you're assuming the draws are independent. So what should you do to check that? Well, all right. One way to check it is to make sure that there's no pattern or grouping. You want random draws, right? So, okay, so here's how this is the ideal plot, this elliptical shaped plot, right? Like this. And this is good. This is what we've been doing. But let's say you have patterns or something. What do I mean by that? I mean like groupings maybe. Like an easy way to see it is what if you had lots of sets of identical twins or something? Well, then you really wouldn't have as big a sample size as you have, because if you know one twin, you pretty much know the other on a lot of measurements, things like that. So if you have like little groupings, like almost the same, like if you see that pattern and then random dots, that's a bad sign that things aren't independent, something like that. So like groupings or little clusters of like that. So that would be bad. That would show that they're not independent. Usually it's time-dependent data that you have where the errors are all grouped together. They're either really high, as you go through that's where this comes in a lot, this violation of independence. All right, and the other, or if you don't have a random sample. And the other thing that you have to, in order to get a standard error of the slope, remember we're using it for all the, okay, so the standard error of the slope, you need this equal variability of errors. What does that even mean? What you don't want is something like This would look bad. You don't, good would be like that. That's good, the same. But bad would be like a sort of fan-shaped thing where you have very little error there, and then you have huge error as x gets bigger, your error gets bigger. You see this a lot, actually. So it's sort of like this. The fan-shaped thing would be bad. It would violate equal variability across the x's. So here's your x's and here's your y, there's your regression line. You have much bigger errors here than you do at other parts. And why is that? You want equal variability, called, people often say homoscedasticity. Homo meaning same, like as in homosexual, and scedasticity meaning spread. And if you have something like this, it's heteroscedasticity is what it's called. And it's bad because think about how the scatter affects the slope. Like really changing y in the middle doesn't affect it nearly as much as like a seesaw is changing it at the ends. So you're just going to get, if you have something like this, it's this, you can't get a good standard error because you don't know where you are along how much change is happening. So this is, you really need to have pretty equal variability. I'll call that, you'll see this word a lot, homo. Homo means same, and variability is scedasticity. So that's S. I'm not going to test you on this, but it might be useful. Scedasticity. Homo and then scedasticity. All right. So that's where these two assumptions come in when you use these. Okay? So basically, what you want to do is usually check the residual plots for this rather than the scatter plot, just because you can see them better. You can expand this scale, and sometimes there's tiny little differences and you don't really see it until you expand this scale. So, so what does it say? Now attach a standard error to your slope. Sure, we can do that. So to your sample slope. What was our sample slope? So we just want to say, all I'm asking is take your sample slope and attach a standard error of the slope to it. And we're going to use these to build confidence intervals for our slope. So in this case, we already got 0.67, and plus or minus, we have to do the standard error of the slope. All right, so let's calculate it over here. So standard error of the slope. Well, I know in the denominator, a standard error is, whoa, shoot, I just did what I thought they fixed this, darn. Okay, I'll come back. It's my hands touching something down here that I shouldn't have touched. Anyway, I want you to think about it. Okay, so standard error, I think, is like a standard deviation. So you put standard error, standard deviation. We're talking about errors around the slopes. That's going to go in the numerator. And then square root of n is in the denominator. So you can remember it that way. But let's first get some clarity here. So what I wanted to say was, okay, so standard error, standard deviation, and it's standard deviation of the errors. That's what that says, errors, over the square root of n. And when you do this, you'd say, oh, square root of 1 minus r squared times the standard deviation of y over the square root of n. You realize standard deviation of x is missing. Now, look, you have a lot to remember. So this will be given to you on exam 2, but I just sort of want to make it intuitive to you anyway. So this will, why don't we write that up here so you don't worry about it too much, that this formula right here will be given to you on exam 2. All right. And now let's calculate it. All right. So we did it before. We did the standard from the previous page. We already had the standard deviation of the errors. That was 8.24, right? So that was 8.24. Over the square root of 100. And then we have to multiply it by what? I'm looking all over on this, using the same thing, 10.3. Whoops, no. I have to multiply it by SD 9 point what? I better remember it. I'm going back to look at it. Thank you for shouting out. Not 10.3. I want x, standard deviation of the x's, so it's 9.2. Does everybody understand that? Thank you for catching my mistake. Wow, I was going to write times. Okay, so times 9.2. And when I did that, I got 0.09. If I didn't know that, I could have gone back to scratch and gone square root of 1 minus r squared. Oh, all right, so it's just that. Plus or minus 0.09. All right, and if you forget where we did this, this was page 113 is where we did that and that. So if we wanted to put upper and lower limits, we'd subtract. So we'd get 0.58, and we'd add 0.76. That would be our upper and lower limits. Sorry, that's messy. Can everybody read that? Square root of 100, that's n, 10 times 9.2. So it's 8.24 over 99.2. Any questions? So, as you might expect, we are going to use that to build confidence intervals. So if you just look at this, what type, do you see we're just doing one standard error? That's going to be, what do you think? A 8% confidence interval for our population slope, right? And if we added 2 of those, it's going to be a 95% confidence interval, et cetera, et cetera. And that's what we're doing in chapter 25. So might as well just look at it. Chapter 25. Okay, inference, finally, confidence intervals. So that's what we're just going to be doing. All right, why don't we, when it's still in our brain, why don't we just, before we read all the theory, let's just do this. In general, okay. Do they have any questions? Let's see if we can just jump into this, and then we'll look at the theory. Suppose we wanted to be about 80% sure that the true population slope lies in our confidence interval. How many standard errors do we need to attach to our sample slope? Same problem. So we want an 80% confidence interval. That's going to be 0.67 plus and minus something times our standard error for the slope, which was 0.09. And they're just asking us what goes in there. So 80%, what would we do? We'd have to just say, okay, 80% would be 80% in the middle. And I happen to know it's between 1.3 and negative 1.3. So that's the Z star, the critical value for Z corresponding to 80%. So that's what we'd put right in here. And then we'd get our upper and lower limits of 0.553 to 0.787. And a 90% and a 95, how would we do that? So the 90% confidence interval is going to be what? 0.67 plus or minus. Do you remember what 90% is? 90%, let's just use 1.65, so we do the same thing. Okay, and a 95%, you know that one. That's just going to be this, plus or minus 2, 0.09. All right, now let's think about why we can do this. Okay, so all we're doing, first of all, we're using the normal curve. Why can we use the normal curve? What can we? It's because of the central limit theorem. If our sample size is big enough, then we can think of the errors, the independent, all those random errors, as being the sum of n independent errors. And the sum, remember the probability histogram for the sum, the average, and the percent follows the normal curve as long as n is large enough. So we don't even have to assume normality here. This is key. We don't. We can just go ahead and use the normal curve without assuming normality of the errors. That fourth assumption, normality of the errors that we talked about, not only do they need to be independent and equal variance, but they also should be normal. That enables us in small samples to use, that's when we will be needed for the t. But if you're not using the t, if you have a big enough sample, you don't need that normality of the errors. Okay, so we have a big enough sample here, so we're fine looking at this scatter plot. So confidence intervals for the slope. So what are we doing? Remember, we're basically saying some confidence interval is going to be the sample slope plus or minus some z star here times our standard error for the slope. Okay, and that corresponds to what level? To some percent confidence. You know, the z star corresponding to whatever percent goes in here. Okay? Now, what else do you need to know for this? Let's just reiterate that the standard error of the slope is going to be equal to those SD errors over the square root of n times SDX. And another way of thinking of it is the square root of 1 minus r squared over the square root of n times SDY over SDX. Those are the same. All right, so that's what we're using here. And now we're saying that it's going to follow the same, basically the central limit theorem. So let's think about what we're talking about. So we're saying there's this true beta. I'm going to say, this is our z, and here's our slope. We're talking about what this is the sampling, the normal curve is the sampling distribution of the sample slope. The idea is there's some true population slope with the Greek letter here, beta, that corresponds right here. That's what if we sample from a population and get these different regression, different slopes, well, the true population, if we did that over and over again, our sampling distribution would be centered right here at beta, the true population slope, and then 68% of the time we'd be in 1 and -1 standard error of the slope, and here we'd be -2 and 2. And this is 68% of the time. Whoops. And this is 95% of the time between 2 and -2. All right, that's all we're doing. And so that's saying what we've been talking about a lot. All right, I think we're good. I think we filled everything in here. And, okay, so what can we apply that to? We can only apply it to the population that we sampled from. So a 95% confidence interval for the slope, let's first make sure. 95%, let's see what that is. So 0.67 minus, all right, so that would be between 0.49, lower limit, and 0.85. So these all ask us, these are the right limits, but to which we can be 95% sure that what? That if we looked at the regression equation predicting final scores from exam scores for all female students would be in that interval? No. It's for all 2000 Stat 100 students because this is the only one. It's not for any it's not for any subgroup because the subgroups could have completely different errors around them, and it's not for a different, this is Stat 200, so no. So let's just write that down. We've looked at that before, that the confidence interval can only be applied to the population the sample was randomly drawn from. You can't apply it to a wider population. Most people know that, but you also can't, or another population, but you also can't apply it to a restricted population, to a more narrow population. Okay, so not a wider or more narrow one. Okay, so basically the idea is that our intervals, these intervals capture the true population population slope a certain percentage of the time. So if 100 pollsters all took 95% confidence intervals, about 95% of them would capture the true slope. That's the idea. And we're gonna, that same idea, next time we'll do the t. We'll just do a tweak on this, and that's where we have to have normality of the errors. Our fourth assumption comes in. So that's it. And you have the homework that's due Thursday doesn't cover this. This will come up. I think this is on the homework. I think it's going to be next week, so I better post it right away. Okay, that's it. And everybody, if you have a question on your own exam, come up and, or if you have any question on your own exam, I can help you with it.